books, and I just wanted to briefly go over the lab 3. So one thing to mention, this is exactly the same emulator that they have, that the professor provided us with. It's just in my local machine, and I just added a beautiful gradient so that I don't want to kill myself in my bathroom while I go through the whole thing. All right, so let's go through this. What does the code do first? Let's just walk through the entire code, and then I can show you the actual thing that happens that is not expected when you first do the lab. So what happens here on the first line, it says load this number, which is a hexadecimal number, load that into the accumulator. This A register is the accumulator, and this is, you could think of it as a variable in a programming language. However, it's used mainly for arithmetic operations. It's called the accumulator. All right, so we load this number in the accumulator, and then we say store that number in the accumulator at this address. And the rest is clear, I hope. These are doing the same things. We're just adding this, and this. These four numbers. That is in hexadecimal 1, 5, 2, and 3. Oh, no. Actually, yeah, it is 2 and 3. All right, so that's what it does. It stores those numbers in those memory locations, and then it starts the routine, what it really does, it starts to add the numbers, the first set of numbers, and then the second set of numbers, and then it subtracts from the first sum the second sum. But we could go over that quickly. So it loads into the accumulator whatever is stored in this address, because at the top we've overwritten the accumulator, and we've been reusing that so that we don't have to use too many variables to, store information. So we're going to do that again. We're going to use that accumulator register. We're going to have this value. We're going to take from that value whatever value is stored here, and then we're going to store it at the location 804. So this is pretty simple. I hope that you can see what's going on there, right? And then we load the information stored at the 802 location into the accumulator again. We add to that number whatever is located at 803, and then we store it at 805. So if we run and we go down there, we can see this is where those two numbers are. Now we have to take from 6, 5, which this is in hexadecimal, but we will see. Oops, what did I do? Okay, so let's see what happens when we do that. This is where the issue is, right? It loads this number, which is the 6, right? And then it loads 805, memory location 805. Actually, it doesn't load that. It just takes that number from the accumulator, because you see this doesn't mention the A right here, but it doesn't have to, because it already knows it needs to take that number from the accumulator. This accumulator is the arithmetic register. When there is an instruction set that says add this number stored at this location, it knows to add that number to the accumulator. It doesn't have to be explicitly shown like in your average programming language. So, all right, so, and then it stores that thing in here. But the problem here is that the way that the microprocessor actually does this whole operation, you need to set the carry flag to actually make this work correctly. And I'm gonna go over my laptop, my iPad, and I'm going to show you exactly how it does that and why we actually have that issue. But let me quickly actually show how you can fix it. All right, I'm going to add right here SEC, which means set carry, and I'm going to assemble and run again. And when we go down, we can see that the correct number is here, 01. That's what it should have stored here, but it wasn't doing that because there's an issue when you're subtracting numbers. And I'm going to go over my iPad, and I'm going to show you exactly what was happening. And I think it'll be clear for you why this is necessary. All right, let's go briefly over the arithmetic instructions that we're dealing with. So we have ADC and we have SBC, right? The issue with the carry flag, and the reason why it exists, is because sometimes we might add numbers that do not fit in 8 bits. Let me show you an example so that we can actually understand what's going on. Let's say I wanted to add, and this is, I'm going to talk about unsigned numbers at the moment. Let's say I wanted to add 250 to 200, right? And I would result, this is in 10, this is decimals, right? This is in decimals, so I would get 450. And let's say I wanted to do that in binary. How would I do it? Let me write this down. 1, 1, 1, 1. And let me see, 1, 0, 1, 0, right? And the other number is 1, 1, 0, 0. I got this a little messy. Let me just move that over there. Great. And the other number is 1, 0, 1, 0. Let me see if that is correct. I got it. All right, wonderful. So if we wanted to add these numbers, how would we do it? Let's actually go through the operation and see how it goes, right? 0 plus 0 is 0. 1 plus 0 is 1. 0, 0 is 1. Now, 1 plus 1 is going to be 0 right here. However, we're going to carry over 1. This is going to result in 0 again. We're carrying over the 1. 0 again, carrying over the 1. Now, we got to be careful here. If we add these two, we're going to result in a 0, and we carry over the 1, but we still have this one right here, right? So it is going to go down here. This is going to carry over, and the same situation again. These two are going to add up to 0, but we're going to carry over, and this 1 is going to go down here, right there, right? Let me clean that up. And so we have that carry right there. And that carry is going to go down here. But what we need to realize, what we need to notice, we are actually out of bounds. This is the 4 bits. This is the other 4 bits. So this entire thing is the actual 8 bits that we're able to store in the register and in the memory address, right? So this extra number that was 1, that was carried, it is actually going to trigger the carry flag, right? It's going to set the carry flag. Why is that useful? It is useful because if we wanted to store a number that we couldn't store in 8 bits, which is like, this is the 8 bits, right? If we are not able to store the value in 8 bits, we can use 2 memory addresses. Let's say we wanted to store this number in the memory address 806. Of course, this is in hexadecimals. Let's say we wanted to store it here, but we know that we have the carry number, and we couldn't store that in the 8 bits. So it has been, the carry flag has been set. Now, what it's going to do, we can actually utilize the next bit in the memory, and we can set that number to which is going to be 7. We can store the rest in 807. So in this way, by utilizing both of these memory addresses, we can store a number that does not fit in a byte, which is 8 bits, right? So we're essentially making use of 2 8 bits, which is going to be the 16-bit to store a number that's larger than 8 bits. All right, so now we got that out of the way. We understand why ADC might result in the carry flag being set. Now, when it comes to subtraction, it is a bit weird. Okay, it is slightly different because the subtraction kind of does the opposite. Let me actually try to see if I can. Let me think. Let me try to do the thing. What we did, right? 6 minus 5. This is what we were doing in the lab, and we should be getting 1, but instead we're getting something else. Let me write it down. So it's going to be 0, 0, 0, 0, for 6, right? So it's 0. I think it is going to be 0 again. Let me just write that down so that I don't make any mistakes. 1, 2, for 8. So it's going to be these two, right? Correct. All right, so that's going to be what it is. And this is what I should have done. That's 1, 1, and 0, right? I think that makes sense. I'm not sure. Let me just check real quick. 1, 2, 4. Yes, these two are active, so that is the 6. All right, let's go. I always try to make sure that I don't have any mistakes because my brain is not that fast, and I'm trying to, compensate that with a bunch of checks. All right, so if this is, this is 1, 2, 4. So yeah, all right, great. That is 5. Now, what is going to happen now? We're trying to subtract these numbers. The way the microprocessor does this is by doing the 2's complement of this. It inverts that and it adds 1 to it, and then it adds that number to this. So let's go ahead and do that. Let's go ahead and do that operation. So 0, 0. I'm just copying the number at the top, and I'm going to invert the other thing. So so this is the number at the top, and then I'm going to copy the other number, but I'm going to invert this. All right. The way that works is by making every 0 into 1s. Every 0 turns into a 1, and every 1 is going to turn into a 0. All right, this is 1, this is 0. That makes sense, right? Let's check so that we don't have any mistakes. All right, correct, that is good. But then you're going to add to that a 1. So this entire operation is the 2's complement. I think that's what it's called. I'm not exactly sure, but I think that's what it was. It's in the book. If we read the Zeit books, we can learn more about this process. So now what happens is we're going to actually perform the operations. It's going to be 1. This is going to be a 0, carry over the 1. So it's a 0, carry over the 1, 0, carry over the 1, 0, carry over the 1, and 0, carry over the 1, and we are just going to go like that. But we just needed to, we just need to look at these at 8 bits, right? We just care about the 8 bits. Do I have more? Yeah, that's good. No, that's good. So what do we have here? We have 1, which is the correct result, right? But when we did this in the actual emulator, we were getting 0. Now, why were we getting 0? The reason why we were getting 0 is because the carry flag was 0. Let me explain that again. It's very confusing. I know. Carry flag. If the carry flag is 0, which means it is not set. If the carry flag is 0, what it is going to do, it's going to think that there was a borrow, so it's going to say -1, and what it'll do, it'll cancel out this operation right here. So we're going to end up with a 0 right here, and we're going to have the incorrect result. This is a bit confusing, but it is how it works. When we're doing the addition, the carry flag is going to use that information to store the additional value into the next memory address, or the one that you actually specify, right? But when we're doing a subtraction, let me actually try to give these. This is sub, this is add, right? Add. ADC, this is the, let me just give it the actual things, SBC. So what the problem is here is that this works the opposite for subtractions. When the carry flag is 0, it is going to think that there was a borrow, and it's going to take 1 away from this, so the the two's complement is not a true two's complement, right? It actually takes that one that we really need to have there. This is why whenever you do a subtraction using the SBC, you want to set the carry flag. You want to say SEC, and then you do the SBC, all right? So what this is going to do right here, what this is going to do here is going to set the carry flag, set carry, which means that the carry flag is going to be 1. In this case, what we want to do, we want to think about this in terms of, let me think. Yeah, it is pretty much the not borrow thing. When you add 1, when you actually set the carry flag, it says no borrow, right? No borrow. All right, so that's pretty much it. You just have to remember that every time you do a subtraction, you have to set the SEC. When you're doing the SBC, you have to set the SEC to set the carry so that it knows there is no borrow. This is something that it's very confusing, that because on one hand, when you're doing in the ADC, when you're doing an addition, it is the carry flag, but when you're doing the subtraction, it is the no borrow flag if it is set. That's pretty much it. And I will actually link a reading at the bottom of the description, and hopefully that'll help out with this information. Also, in the lab, at the very bottom, the professor has some explanation, which is not clear. I'll give you that because it's pretty. He has the symbolic representation for this instruction, which does not help a whole lot, because if you're not familiar with symbolic representations, or if you're not familiar what it's really talking about, it's not clear. And I wish the professor was, explained it a little in simpler terms, but this is pretty much what it is.